Yeah, let's go ahead. Yeah, it's 5:35 already. So welcome to the recitation. Today I'm gonna cover Frank Wolf, which Sufert is going to also cover in class. So this is more just a like preview of the lecture. So I'm gonna go through what is a Frank Wolf algorithm and what are the problems that they solve, and what are the advantages of Frank Wolf comparing to other optimization frameworks. And after doing that, I'll give some hints on the hack of why it works, and then give a convergence proof. So that's basically what I'm going to cover in the recitation today. So. Yeah, this is based on the Revisiting Frank Wolf projection-free sparse convex optimization paper by Martin Jaggi. It should be 2013 SML paper.
Not 13,
no?
Or
yeah, something like that. Hey, yeah, you're not missing anything. We just started. So basically, we're gonna cover Frank Wolf and give some examples of the kind of problem it can efficiently solve, and then prove its convergence. So this is a general convex optimization form that Frank Wolf tried to solve. So we need the function f to be convex, and it needs to be continuous, and also need to be like first order differentiable. And for this domain D that we are optimizing on, we need it to be compact and convex, and that's only two like components, and we need like an inner product to be defined on the space. What?
when you're forming the gradient and then solving the subset,
Mm-hmm.
D is a linear sort of system, then
If D is like D is a bounded subset of the Hilbert space. Yeah. So typically the cases when Frank Wolf works well, this D is typically small, and it's like a convex Hall of certain atomic sets. So yeah, I'll get to that. So to understand the iterations, before I actually write the algorithm, I'm gonna like draw the graph here. This is a function we are trying to optimize over, and this is the D. Say this is x greater equals to something. Yeah, this is basically D, and this is a function fx. So the algorithm of Frank Wolf is basically like, hey, how much? There's a value finding analogy of this. So basically, at any point we start, then we find a gradient, and then we try to go as fast as we can on the gradient until we hit a wall, and then we trace back and stop somewhere in the middle with a step size like on the ratio of gamma, and we call this point S. And then we update the point to here, and this is x1. So we keep doing this, and that basically gives us like the Frank Wolf algorithm. Specifically, the algorithm is like we have x 0 to D, and we loop. And iteratively, we want to solve like this subroutine. This is argument optimization. And then with a parameter gamma equals to, typically people choose like 2 over 2 plus k. And we update the step by doing this. And we loop until convergence. So when we do this, we only need like the first order information of the function, and this is essentially if D is like a polytope, this is essentially LP. So it's considered more convenient than like the proximal map when you need to minimize. Sometimes you need to minimize like a projected least square kind of thing when you have an indicator function on the D here. So yeah, and another interpretation of this is that we can write this out as a first order approximation of the original function x by doing the Taylor series of expansion, and because the function is convex, this always gives a lower estimate of fx. And yeah, so the two-step is basically to minimize over the linearized version of the function in the space D, and the second step is to interpolate between the optimal solution we find, which is S, and the previous step, and do like an interpolation between these two and stop somewhere in the middle. So I would say that for the algorithm, just remember this picture, and it tells you everything about the classic Frank-Wolf. And more current version of this involves like solving this thing only up to like additive error. So approximately solving the linear oracle is good enough. And we can prove convergence about it and in a short while. So is everyone clear about what the algorithm does and the kind of problem it solves? I haven't given any examples, which will come real soon. So let me just list the key advantage of Frank-Wolf algorithm compared to others. So like I said, it needs like the gradient only, and second, we can like easily compute a formal duality gap in every iteration. This is central in the proof of its convergence. So I'm gonna talk about this later, yeah, and it induces certain structures, like sparsities, and the entire solution path. Suppose we are minimizing this over x, like the L1 norm of x smaller than something, then the entire, if the actual solution is sparse, then the entire solution path will be sparse. So it's like orthogonal matching pursuit type of algorithm when we add like one coordinate into the solution and keep iterating. Well, yeah, and it is invariant under any affine transformations. So methods like gradient descent, they need to be well conditioned before it can be like really fast. But for this algorithm, its convergence guarantee holds for any affine transformation of the compact space it's optimizing over and the corresponding function. So you do not need to do any preconditioning. It wouldn't help. And but on the other hand, if the problem is poorly conditioned, well, you still get the same rate. So I call this invariance. And lastly, it's guaranteed for like a proximal solution to the key subroutine. So it can be additive error. It can also be like multiplicative error. So they have a almost identical analysis for both these two scenarios. So let me give you like 3 representative examples of the problem this solve. The first, like constrained version of the matrix completion, noisy matrix completion. Suppose M is a measurement and X is the matrix we want to impute, and omega is a set of the observed entries. So we are minimizing the Frobenius norm subject to the nuclear norm of X needs to be smaller than some constant, let's say tau. So this defines D, and this defines F, and within D, why don't we just write the form here? So if we want to, in fact, let me write the other example and do it together. So this is like the original version of the lasso with a constraint. For any constraint of this norm form, we can write the subroutine as we want to minimize some s, and this part is a gradient. Let me just replace this with y for convenience. Want to minimize this subject to the s norm. Some norm can be nuclear norm. It can also be one norm. Needs to be smaller than tau. And because this is just inner product, this being smaller than tau is equivalent to smaller than 1. And then suppose we add a negative sign here, and we have a max here. What do we get? We simply get the dual norm, right? So the optimal solution is a S that attains the dual norm. So for these two specific problem, we only need to, in each step, we only need to find the dominating singular vectors and these corresponding singular values, and then take the rank 1 approximation of this, and we're done. So which can be efficiently solved by Lanczos projection. And it's more efficient than solving the full SVD or even sparse SVD. And for this, we only need to go through all the data points in this y, negative y, and find the one with the largest magnitude. Because the dual norm of the L1 norm is just the infinity norm. So is everything clear? I add a negative sign here. So minimizing sy is equivalent to maximizing s negative y. So this negative y is something you put into the dual norm. Y is a gradient of fx at point xk.
Yeah, so just think of that as y minus ax.
Yeah.
So finding the largest element of y.
Yeah.
He's just confusing what y is. So maybe you should write that y as y minus ax.
Okay.
Or as d omega x minus s of the gradient. Whatever the gradient is.
Yeah. This is something known.
Oh, I see.
Yeah, we are optimizing over s.
And I was just confused because there is y minus ax.
Oh, sorry. Sorry. Yeah, that's the point. Yeah. Okay. Yeah, it doesn't matter. As long as you guys all get the point.
Yeah. And the constraint is like.
The constraint is the norm. For this problem, this constraint is a nuclear norm. And for this constraint, it's a one norm. right?
Arc min over S in D. Yeah. In this case, D is
Yeah. You can always scale it because this is linear, so it doesn't matter, and it gives you precisely the dual norm. And another example, using Lanczos algorithm. Yeah, to ensure X has low trace norm. So which is something we want, say, in recommendation system. Yeah. This is different from if we minimize in this thing and plus a nuclear norm regularization term, but it's somehow like equivalent for 1 tau, and there exists some regularization parameter up here. Yeah. So yeah, but Frank-Wolf. Yeah. But Frank-Wolf is not able to solve the other problem. And also, suppose we try to solve these two problems using like proximal gradient algorithm. In each iteration, we need to solve SVD and use like the shrinkage operator. So it's n cube. Yeah.
So can you walk through again what's the operation if you can update what you're talking about? So you're solving the dual norm,
No. You are solving the dual norm. You know the solution is that you know the optimal value is a dual norm of this y, right? So something that attains, like let me write it this way. Let me use S smaller than one norm, y infinity norm, right? Right. Yeah, the S that attains this upper bound is just the maximum entry, absolute entry in Y. So if you take S to be max, the element in Y that has a maximum element, then you can maximize this thing, which gives you the optimal solution to that. And this arc max and equivalent to arc min, so it gives you the solution to this problem. Yeah, so it's like you only need to go through Y.
Yeah, so computing this doesn't save you much, right? The software actually.
Yeah. For this, it doesn't save you much. For this, it doesn't save you much, but for nuclear norm, it saves you a lot. And let me give you one more example here before we proceed to talk about the duality gap. So this is like an assignment problem. Suppose we have n workers, and we have n tasks, and we want to assign each worker to work on precisely one of the tasks. So it's like an and we have some objective function we want to maximize or minimize. Say we want to max the profit minus the cost subject to like each worker work on each task. So in math, this is like optimizing the indices of the worker over a permutation. To construct a permutation matrix that gives you the maximum profit minus cost. So suppose we have an assignment matrix X, and this is assumed to be a permutation matrix. And if we are able to solve this optimization problem, we solved the assignment problem here. But the thing is, X being a permutation matrix is not a convex constraint. So if we like take the relaxation, convex relaxation of this, we get something called a Birkhoff polytope. And this Birkhoff polytope is the same as the doubly stochastic matrices if we consider the assignment matrix. And it's simply all the entries are greater than 0, and each and every row and column sum to 1. So that's the tight convex relaxation of the permutation matrix. And so in the original like problem, we have like an exponential number of permutation matrices to go through. But if we do the relaxation, we only have like n squared number of linear constraints, and solving each sub-problem is a linear programming problem. And they said in the paper that there is a version of the Hungarian algorithm to do this exactly, and there are certain guarantees that this gives you the solution to the original assignment problem. And using Frank Wolf, like each sub-iteration in there can be solved in n-cube time. Yeah. So they have a whole lot of such examples in their paper, summarized in table 1 and also table 2. So if you take a look, and maybe some of your own problems can be put in their framework and try to like write 10 lines code and try it out. So that's enough of the examples. Are there anything that's not clear? Okay, so I'm going to explain the second point, the duality gap. So the duality gap is defined to be a function of at every point within D. So let this x be some point in some feasible point. And gx is a function that gives you the duality gap. It's not the Lagrangian duality gap, but it serves the same purpose, and it gives you the it gives you an upper bound of the difference between your current fx and the optimal fx star. So if you can show the duality gap go to 0, you are essentially certifying the convergence. And the point is this duality gap can be computed without additional effort in every iteration. So it is written like this. It's a maximum over all S in D. X minus S. So that's basically it. If we like this X and this grad fx, they're not related to the argument S is in D, so we can take it out, and then we have a max over minus S, the gradient. That is exactly something that we solve in every iteration. So we solve that, we evaluate the objective function, then we add x inner product grad fx, and then we get like a duality gap. So I haven't tell you why this is a duality gap. So let's try to see that. Okay, first of all, the linear form, the linear expansion of x is always smaller than the original function because the function is convex, right? So this is basically a first order Taylor expansion of fs, and because of that, we know it is always smaller than fs. And well, if we take this thing to the other side, and then minus the optimal objective value, then we get right? And this gx is the upper bound of that because we take optimal, we take the maximum over this part. So this gx always gives us an upper bound of that, and it is computable. So when we try to determine whether the algorithm has converged or not, we can use this gx as a measure of convergence. So
you're assuming that the value is positive. Yeah, what you're assuming? Something
where?
You're assuming fx optimal is positive.
Oh, I
Otherwise
haven't.
you have to add that term.
Yeah. Sorry. Yeah. Wait. Oh, yeah. There's another. Oh, it's not like that. Sorry, there's one other step. We do another Taylor expansion here. Yeah, we use the property again by taking S star to be S. You see, we take this S to be X star and take this to the other side and invert the sign here and put this to the other side. Then we get that. And since X star is in the feasible domain, then this thing is smaller than if we optimize S over the entire D, and that gives us like the GX. Yeah. Now it should be making sense. Okay. Yeah. There's a discussion in the other paper that suggests that this GX is a special form of the Finchel duality gap. And if we take the convex conjugate of the fx and then plug this thing into the convex conjugate of that, convex conjugate of not fx but fx plus the indicator function of x is in D. This indicator function is the zero infinity indicator function. And if we take the Finchel conjugate of this and plug this into the conjugate, then we take the difference, then it gives you exactly this GX. So that's just another interpretation from something we learned in the class. Okay.
So the normal Finchel conjugate is not constrained, right?
Yeah. That's why I add this.
Okay.
That's why I add this indicator function. Okay. Why is it called duality gap? Yeah. Because the thing about duality gap is that you construct some dual variable, and then you evaluate the dual optimization problem, and then you take the difference between the primal and the dual, and that gives you some duality gap. for the current iteration, and that's an upper bound for the difference between your current objective value and the optimal objective value. So this says that having this gx, it's if this gx goes to 0, it certifies the optimality. Yeah. So. Yeah, the duality comes into the picture if you take a look at this interpretation in terms of the Fincher duality. Yeah. So did we manage to cover? Okay. Yeah. So now let me write approximation. Suppose we can only solve that subroutine approximately, then we assume that we have a procedure that we are able to find an S such that this chalk is yeah. So we assume that in every iteration we can solve this up to an additive error of this amount. CF is something I will explain. It's called the curvature, and this delta is like the error factor, and this gamma is there even a gamma here? Yeah, I assume there is. This gamma is just something. It's just a step size. That's the step size of every iteration. Yeah, and the multiplicative approximation is more realistic because it doesn't assume the numerical accuracy goes down each time with gamma. That is simply to multiply something like a like a V here, and this V is assumed to be somewhere between 0 and 1. So curvature. So curvature is like a measure of nonlinearity, and it is closely related to the Lipschitz constant, gradient Lipschitz constant. And suppose the function we try to minimize this fx is actually linear, then this curvature is 0, and it is defined. It is defined to be sup over x, all x or s in D, and for any gamma, 0 and 1, and this is a very much the most critical assumptions one needs to make in Frank Wolf's convergence analysis. So basically, we choose x and s from the domain D, and there's a dummy variable y where we then we choose an arbitrary like line search coefficient gamma, and then we add this gamma s minus x into y. So y can be considered as a update we want to go to, and x is a current value f current value xk. minus yeah, this is the definition of the curvature. What's delta fx is a gradient of this gamma is just a step size, and delta is a constant that gives you the additive approximation. So we don't need to solve the problem to exactly, but up to this amount of additive error on the objective function.
I guess the delta goes into the convergence there.
Yeah, delta goes into the constant of the convergence rate. Yeah, it's not in the rate, but in the constant up there. So it's not really a huge concern as long as it's smaller than CF. Yeah, the gamma is a step size in the algorithm over there. Yeah. So an implication of this is a very key thing that we will use in the convergence proof. That is, for any x and y in D and or any x or s, it doesn't matter because one x and s and gamma determines y uniquely, and for any gamma 2, 0, and 1, and we have this. So basically, we multiply the coefficient to the other side, and then represent this soup as an inequality. So that's all it does. And this is an inequality that we are going to use in the convergence proof. So what is their claim? Yeah, any Frank-Wolf have a curvature assumption. And yeah, for any Frank-Wolf, it has this thing in it, and you'll see that it shows up in the theorem. And the smaller the curvature, the faster the Frank-Wolf is, but it's just a constant thing, so it doesn't really affect the actual convergence rate. Yeah, another thing that worth mentioning is that this thing is upper bounded by Lipschitz constant of the gradient. This is a gradient Lipschitz constant times something that is a diameter of the domain. In terms of the norm, this Lipschitz constant is assumed in. So this suggests that Frank-Wolf is better at optimizing over like a domain with a small radius. So it's basically a abundantness assumption plus Lipschitz assumption gives you a uniform curvature constant. So this may help you guys to connect this to other optimization techniques. What? No. Yeah, it's the same norm. So the theorem is basically for any iterate number k, the xk obeys. This is only the primal convergence theorem. They also have like a primal dual convergence theorem by showing the duality gap goes to 0. But for simplicity, I'm only going to do this today. Okay, so like you can see, this is sublinear convergence rate, 1 over k. It's not very awesome, but you see they have the approximation ratio here, 1 plus delta. So we do not need to solve the subproblem exactly. And this theorem works for both the exact version, where we simply take delta to be 0, the approximate version, and there are 2 other versions called line search version, which is algorithm 3, and the fully corrective version, which they called algorithm 4. So the line search is basically, instead of assuming this fixed step size, we take the line search over the entire gamma between 0 and 1 and try to find the updates that give you the least objective value. And the fully corrective version is to keep track of all the s in the earlier estimates and try to optimize this thing jointly over the subspace spanned by all the previous s. And that gives you something that is very OMP-like. So this theorem is stated for all the algorithms, algorithm 1, 2, 3, 4 that involves all of Frank Wolf's. Orthogonal matching pursuit. It's something in signal processing used to recover the sparse support. So it's basically a lasso solver. A greedy algorithm. And it's interesting that many of those greedy algorithms can be thought of as a special case of Frank Wolf, as they claimed in the paper. So maybe I have time to cover the key lemma for the convergence proof, or I can simply state the lemma and then go to the convergence proof. So we started 10 minutes late, so I assume we can run over time for 10 minutes. So the lemma says that if S is an approximate solution according to that criteria. Yeah, I didn't talk about the multiplicative version because it's not in this paper but in the other paper. But yeah, the analysis is basically the same. Why?
Because you want the gap to be as close as possible.
Yes, but this V means that you cannot get optimal. Like when V equals 1 and we do not have this block, then we will have and then we get the exact optimal solution to this problem.
Yeah.
So when V is between 0 and 1, that means that we only have an approximation. Is that making sense?
So
We
we want to solve the objective there, right?
want to solve the objective here, but we can't solve that unless we add some slack at the back. So this S is an approximate solution to this problem, either up to an additive error or up to a multiplicative error. If we invert this V and multiply on the right-hand side, then we get something that is greater than 1, which justifies that it's an approximation. Yes. If this V is half. So the lemma says that if S is an approximation to defined over there, then the iterate xk plus 1 is then this update step for any gamma between 0 and 1 will give you this inequality. This is the duality gap plus and the approximation constant comes over here. So I'm going to use this half of the blackboard to prove this lemma. And as you can see, this lemma basically gives you an iterate. It's like a recursive kind of thing. So this is a key workhorse for the convergence proof. And the proof is like, first of all, by this star, right? We can take y to be, yeah, let's make some simplification. Let x to be just xk, define y to be xk plus gamma s minus xk. Yeah, and also let dx to be the grad of f(x) at the point of xk. Okay, so by the star over there, we will have this equals to if we expand this thing out, let me be consistent in that basis. Dx. This is simply to expand the inner product term in another chunk. In this inequality, we simply apply the fact that S is an approximate solution by replacing this with the quantity of S that is optimal up to delta times CF times gamma. And because there are a single gamma over there and there's another gamma multiplied in front of the main, then we get a gamma square, and then we combine that term with this term at the very back, and then we get a 1 plus delta gamma square CF over 2. So now we can further combine these two terms, and what do we get? We have something that looks like S minus X in it, and that is something we defined as a duality gap. So we claim that this is actually equal. This is gamma gx. The rest are the same, and that gives our proof to this inequality. Is that right? Okay. And the key idea why we can prove the line search variation and a fully corrective variation of the Frank-Wolf is that the update objective value is always smaller than this, than the specific gamma that we picked to get to this xk plus 1. All right? So having that lemma, proving the actual convergence theorem is quite simple already. So let's assume the difference between the current fx and the optimal objective value to be hx, and then we simply subtract fx star on the both side of this inequality, and we get, and we also like make this entire block gamma square c. Okay, so we will have hx plus 1 equals to hxk minus gamma gxk plus c, and let me call this hk plus 1 and hk. Yeah. Also, by the fact that gk is a duality gap, GK is always greater than hk. That's why we can simply replace this gk with hk. Right? And then we can combine the terms, combine the two terms, and get 1 minus and well, now, the reason why we can replace G with H is here. It's because we showed that this Gx is a duality gap. It is always greater than this, which is basically Hx by definition. So after we have this, the rest is to show the claim in the theorem up there by induction. So for the base case, when k equals to 0, then this gamma 0 equals to 1, and plug this into to this thing, and we will have. We can actually evaluate this h0 exactly equals to f x0 minus f x star. This entire thing is yeah, this is like we try to do Taylor expansion around x star, and because it's optimal, this gradient equals to 0, then this term cancel out, and we are left with that, and we substitute the gamma 0 equals to 1 in here. It's simply half of the curvature vector, and our claim is that that this needs to be smaller than curvature vector, so we get it. The case assumes that we have k. We want to prove that for k plus 1, the inequality in the theorem is also true. This is also, well, very simple just by something here. What we need to do is to, why is gradient 0? Because this inequality is obtained by taking the Taylor expansion around x star. So the gradient at f star is 0 by the optimality condition. Oh, we need the function to be differentiable. Uh-huh. Oh, yeah. Yeah, true. Yeah, I think they probably have a different proof of the base case in their paper. I need to take a look. But basically the idea is to take k equals to 0, evaluate the gamma, and then try to show that the inequality hold for the initial case. So this is not right. Thanks for pointing that out. Yeah, the optimal solution can be on the boundary, so it's usually on the boundary. Yeah. So the iterate when so what we need to do is to simply first replace this hk with what is claimed up there. So we get 1 minus gamma 2c over k plus 2 gamma square c. And we substitute what is gamma in there, because this gamma k equals to k plus 2 over 2. We get 1 minus two c k plus 2, and we have k plus 2 square, and up here is 4c. Yeah, then we multiply this in, and these two terms cancel out, and we get exactly the claim. So. For the base case? Okay. I think maybe that's because by the definition of CF, and we can bound. Maybe we can because the definition of CF is uniform over all the feasible x and x stars in D, then we can upper bound this by another CF, which give us somehow an upper bound. I need to check on the paper.
I think it's just that for any feasible x,
Yeah.
x minus x star and gradient of x star will end up being negative. It's not that gradient of x star will be 0.
Okay.
But if there's any other feasible x, then x minus x star.
Okay. Yeah.
So
Yeah. First order condition of the convex function. Okay.
So it's not that the gradient is 0.
Okay. Yeah. And it's negative. So, yeah. All right. Thanks. So, that's all. And thanks for coming. If you have any questions, yes. I hope everything is clear from the definition and. There's one last thing I'd like to say is that this basically gives us like a recipe of trying to come up with problems that one can use Frankfurt to solve. Like we learned a lot of approximation algorithms in the class, right? Like sketching, like compressed matrix multiplication, and there are also a lot of like combinatorial algorithms like max flow, min cut, and shortest path in a graph, or minimum spanning trees. And if we can somehow formulate those problems as one of the subroutine, and then we can use that to try to come up with a problem that have that subroutine and use Frankfurt to solve it. And this will basically add to the list that Martin Jaggi gave in table 1 and table 2 of the paper. And I hope you can appreciate the structural implication of the method. Since if we update the advantage of using this to solve the lasso type problem is that we never need to store a dense X, because each and every time we only add one single coordinate into the solution set. So X always stays sparse. So memory-wise, it is more, it is better, I guess, than if you do proximal gradient-like algorithm when you solve for least square and then do soft thresholding. Yeah, this is just my thought. Which step? Okay, yeah. It's not a linear combination. It's a convex combination of. Yeah. So if you solve the lasso problem there, and the solution, the S will be a one sparse solution, since we simply take the maximum coordinate. So if we interpolate that with anything else, then at most it will add only one non-zero entries into the xk plus 1. Yeah, the rate is slow. There are linear rate for this tool, but they need additional assumptions and additional steps, such as they often add an away step to the Frankfurt algorithm. So instead of solving this all the time, updating X in this way all the time, sometimes they solve an away step by by basically try to find the other end of the solution. So under some conditions, they use the away step instead of the forward step, and that turns out to help you achieve the linear rate. Yeah, they need strongly convex. They need gradient Lipschitz. And
they often need that the minimizer is in the strict interior of the domain.
yeah,
And then you can see if it's not on the boundary, the minimum is in the strict interior, then you can get convex. Like if you
Yeah.
get linear,
The- yeah, they need additional technical conditions. They also need like additional steps other than the vanilla Frank Wolf algorithm in order to achieve linear rate. Yeah, it's in the other paper. It's not in this.
Alright, fine. These results are very old. Like they're from the 80s. The linear convergence of Frank Wolf is like a very. I mean, in the case where it's
Yeah.
interior, like where there's not convexity, this is from the 80s.
Yeah, and
This got more attention recently because of the sparse connections.
yes,
That for lasso and things like that, your updates are really fast. So if you just stop after k steps, you'll end up with a sparse solution because you only updated k and
yeah.
of your.
The original paper by Frank and Wolf, they already have this result without the approximation. So this is like a reproduction of the same convergence guarantee for different variants of the same algorithm. And the linear rate also appears somewhere in the 80s or even 60s. But recently there are linear convergence papers that assume weaker condition, and they claim that it's more reasonable assumption to make. And people generalize this away step with something else that is close, but is a more optimal way of doing things. And actually all these can be considered as a special case of something called a dual averaging algorithms. Yeah. So you can take a look at the NIPS workshop on Frank Wolf, and their presentations contains a lot of related stuffs and how things evolve in history and why people start to care about this again.
Quite interesting that
Yeah.
actually the Frank, who is Frank Wolf, her name is Marguerite Frank, and she's alive. And they invited her to the workshop, and she was like, she was the first that we started
Cool.
with her at the workshop.
Cool.
She had no idea that this algorithm would become popular in machine learning. She was completely like, oh, I don't know why
Oblivious.
it's such a big deal and things like that. And she works on some other stuff like Lie group algebra and stuff like
Yeah.
that. And she just did this as a side project with Philip Wolff. Like Philip Wolff used to be a guy who was like optimization hardcore.
Uh-huh.
And then like Margaret Frank just she was joined in on the postdoc and then did this. And then after that she just continued working on her math stuff. And like forgot all about optimization. And they got her to this workshop and she's like, I had no idea that there's a workshop named after this algorithm. It's like whatever.
Cool.
It's quite funny.
Yeah. This only require like solving the gradient. So for the large scale optimization, like when we cannot even afford to solve a quadratic optimization, then this is more useful.
For this case, the basis solution consistent of the basis, I mean the non-zero entries that you get, are they solved around?
They have approved for OMP though.
Really?
Yeah.
Yeah, but like after k steps, does that is still consistent? I'm not seeing it.
Yeah, you're talking about support recovery, but we are talking about solving the optimization. If the optimization turn out to like have the optimal solution and also recover the support set, then at least towards the end, when k becomes really large, then we will have the correct support. Yes.
Yeah, we never recover. And like proving like that your support is correct is very hard.
Yeah. Especially proving the support is correct in exactly k steps, I don't know.
No, you're consistent. I know what you meant, but like I mean, even proving that the optimum, if you solve it to the optimum, even proving that is persistent is really hard.
I think they have like.
I mean, they have this stuff. Lasso has this stuff, but it's very hard.
Yeah, I understand.
So like proving it that.
It's okay. You need additional assumption, but the proof is not too hard. You basically construct an infinite series, and the sum will give you a dual certificate, and that certifies the optimality condition, and it gives you a support recovery result. So it's the same for Lasso like method and for matrix completion. So
Typically, the difficulty in the Lasso establishing kind of weak. Like,
okay.
Like the weaker the condition.
Yeah, if you don't assume RIP, then
So
it's
basically there are
hard.
conditions weaker than RIP under which it's won.
Okay.
And then under those it's very hard.
And they are not true in general, I would say.